Hey everyone, my name is Warren and I'm a math and computer science major at the University of Illinois. I'm a Suli intern at PNL, mentored by Bryce Harrop and Claudia Tibaldi. And today, I'm going to be talking to you about flying rivers using machine learning for predicting precipitation. But first, I want you to imagine you're a kid again, sky gazing at the park. Imagine how nice it would be to lay down and take a nap along those fluffy clouds. What are clouds, anyways? I'm sure we all learned as kids that clouds are really made up of a bunch of tiny water droplets and ice crystals. When they condense and get too heavy, they fall to the ground as rain or snow. What you probably didn't know is that most of the water in the air is actually invisible. It's water vapor, a gas you can't see. And there are massive amounts of it floating above us right now in the form of atmospheric rivers. Huge streams in the sky. They carry water from the tropics to the poles. Fun fact, this one from Hawaii to the West Coast is called the Pineapple Express. So how these rivers form is water evaporates near the warmer regions, near the equator, also known as the tropics, which are then channeled into streams by winds from other weather events, such as cyclones, as can be seen in this NASA satellite image. And what you're looking at right here is a snapshot from the DOE's Earth System model, showing how all the atmospheric rivers detected at this time follow this trend of carrying water away from the equator and towards the poles in these mid-latitudes, as you can see. So when these rivers reach land, they're forced upwards by mountains and coastlines, cooling rapidly, releasing massive amounts of precipitation. In fact, 50% of annual rainfall on the coast of many parts of the world are caused by atmospheric rivers. This makes them absolutely vital for our water supply. Half of the water sitting in the US West Coast reservoirs come from atmospheric river events. This is the same water we drink, use to grow crops, and rely on every single day for our basic everyday needs. It can also be a lifeline for areas suffering from drought. Between 1950 and 2010, 75% of droughts in the Pacific Northwest were ended by atmospheric rivers. A single river can refill reservoirs and restore snowpack in just days. But there's a darker side. The same rivers that sustain us can also cause devastating damage. When too much rain falls too quickly, the ground can't absorb it, and this is when flooding happens. For example, in Brisbane, Australia, 2022, they received an atmospheric river event that caused nearly 80% of their annual rainfall in the span of just 1 week. The result was devastating, massive flooding. Over 15,000 homes were destroyed and 9 lives lost. This shows us how the same rivers that fill our reservoirs and end our droughts can just as easily destroy entire cities. It all comes down to intensity and timing. So it's clear that these rivers have massive impacts all over the world, both good and bad. Since the line between blessing and disaster is so fine, it's critical that we can detect them in advance and give people the time they need to prepare for these extreme weather events. Recently, AIs have taken over the world in the form of LLMs, but they're doing more than just answering questions. They're transforming science. We've seen this in biology with AlphaFold solving the protein folding problem. We're also seeing in atmospheric science. In this field, AIs are trained to emulate the patterns of our best physics-based models. With the new machine learning architecture, they're trained on things like wind speed, humidity, temperature, and many other useful variables, all on a global geometry. Our research specifically is looking at an AI that can emulate the DOE's Energy Exascale Earth System model, or E3SM for short. This work is done as part of E3SM's AI group, who train and evaluate these models. How these physics-based models work is they use complex math equations and code to represent everything from large-scale atmospheric dynamics down to microparticle interactions. This results in high accuracy, but the trade-off is the massive amount of compute needed just for a simple simulation. AIs are trained on data instead, and our results show that the emulator achieves similar performance to E3SM when compared on precipitation caused by atmospheric rivers. And it did this while being far less computationally expensive. This means faster, cheaper forecasts. People will be able to more efficiently predict and prepare for future weather events. Water could be rationed out in times of drought, and damage caused by flooding could be mitigated in advance. So, the next time you look at clouds in the sky, think about how this water may have traveled halfway around the world in a flying river. Thank you.